In this video, we'll learn how to do factorization of polynomials of higher degrees. First of all, let's take a look at this example. Suppose now we want to factorize 3x to the power 3 minus 10x squared minus 9x plus 4. In order to factorize this polynomial fx, first of all we should find a factor of fx. In other words, we should find the values of m and n such that mx plus n is a factor of fx. If we can find this factor, then we can factorize this polynomial. If we assume that mx plus n is a factor of fx, that means fx can be expressed in the form of mx plus n times ax squared plus bx plus c, where m, n, a, b, c are integers. If we do expansion, then we should know that the x cubed term should be max cubed, and the constant term here should be nc. Now when we compare the coefficients of x to the power 3, then we should know that ma is equal to 3. And when we compare the constant terms, then we should know that nc is equal to 4. Because m, n, a, b, c are integers, that means now we can conclude that m is actually a factor of 3 and n is a factor of 4. Once we know that m is a factor of 3 and n is a factor of 4, because m is a positive integer, that means m can only be 1 or 3. And because n can be a positive integer or a negative integer, n can be plus or minus 1, plus or minus 2, or plus or minus 4. As a result, we can see that the possible linear factors of fx are x plus or minus 1, x plus or minus 2, x plus or minus 4, 3x plus or minus 1, 3x plus or minus 2, and 3x plus or minus 4. For each of these possible linear factors of fx, we can apply the factor theorem to check whether it is really the factor of fx. That means for x minus 1, we check the value of f1, and because this one is not equal to 0, that means x minus 1 is not a factor of fx. And then for x plus 1, we check the value of f minus 1. For x minus 2, we check f2. For x plus 2, we check f minus 2. So on and so forth. After checking these possible linear factors, we can see that only x plus 1, x minus 4, and 3x minus 1 are actually factors of fx. And now we can conclude that fx is just the product of x plus 1, x minus 4, and 3x minus 1. This is how we can factorize fx by finding all the linear factors. Another way to factorize fx would be like this. We can first of all check x minus 1, it is not a factor, and then we check x plus 1. Once we know that x plus 1 is a factor of fx, we stop the checking process here. When we know that x plus 1 is a factor of fx, that means now we can perform a long division like this, and the remainder should be 0. The quotient in this division is actually another factor of fx. This time it is a quadratic factor. That means now fx can be expressed as x plus 1 times 3x squared minus 13x plus 4. This is already a factorized form of fx. For quadratic expressions, we have already learned how to apply the factor method to do factorization. That means now this expression can be further factorized like this. And this is how we factorize fx, by first finding a factor of fx and then we consider the long division, and afterwards we try to factorize the quadratic factor. Let's take a look at other examples. For example, suppose now I want to factorize x to the power 3 plus 4x squared plus 5x plus 2. Again, we first of all try to list all the possible linear factors of fx. And to find the possible values of m, we take a look at the coefficient of the term with the highest degree, that means x to the power 3. And for n, we just take a look at the constant term. That means m is a factor of 1, that means the coefficient of x to the power 3. And n is a factor of 2, that means the constant term. Because m must be positive and n can be positive or negative, that means all the possible linear factors of fx are x plus 1, x minus 1, x plus 2, and x minus 2. And now we should apply the factor theorem to check these possible linear factors one by one. For x minus 1, it is not a factor. For x plus 1, because f minus 1 is equal to 0, then we can conclude that x plus 1 is a factor of fx. Once we find a factor of fx, we can stop this checking process, and then we can perform a long division. Now the quotient in this division is another factor of fx. That means now fx can be expressed as x plus 1 times x squared plus 3x plus 2. And x squared plus 3x plus 2 can be further factorized, like this. Therefore, we can conclude that fx is equal to x plus 1 squared times x plus 2. And this is the result of the factorization of fx. Finally, let's take a look at this example, the factorization of 2x to the power 3 minus 3x squared minus 32x minus 15. In order to list out all the possible linear factors of fx, first of all, we take a look at the coefficient of the term with the highest degree. That means 2x to the power 3. And then we can conclude that m is a factor of 2. And then for n, it is a factor of the constant term. That means it is a factor of 15. Because m is positive, it can only be 1 or 2. And for n, it can be plus or minus 1, plus or minus 3, plus or minus 5, or plus or minus 15. That means now there are 16 possible linear factors of fx. And then we apply the factor theorem to check these possible linear factors. For x minus 1, it is not a factor. For x plus 1, it is also not a factor. For x plus 3, because now we know that f minus 3 is equal to 0, so we should know that x plus 3 is a factor of fx. Afterwards, we can do division to find another factor of fx. Now the quotient in the division is another factor of fx. That means fx can be expressed as x plus 3 times 2x squared minus 9x minus 5. After further factorizing the quadratic expression 2x squared minus 9x minus 5, we should know that fx can be factorized as x plus 3 times 2x plus 1 times x minus 5. And this is how we can do factorization of polynomials with higher degrees.